Hello, in this video I will be talking about partial saturation sequence, an imaging sequence for MRI applications. I'll first give a brief explanation of this topic and then show one-dimensional signal analysis and two-dimensional image analysis of this sequence, which are made by MATLAB software. So let's begin. This is basically the partial saturation sequence. These are the RF pulses. So there is a sequence of 90-degree RF pulses in order to generate an MRI signal, which then will be reconstructed into an MRI image. And also, this sequence of 90-degree RF pulses is given with a period of TR. So what happens when these pulses are generated, are applied? Firstly, just before the first RF pulse, the magnetization vector is in the z-axis. After the first 90-degree pulse, which is stated here, the magnetization vector is tipped down to the xy plane. This is the excitation part. After this excitation part, the relaxation immediately begins. What happens in this relaxation is there are two relaxations, longitudinal and transverse. Longitudinal relaxation happens in this direction, so the magnetization vector is going in the positive z-axis direction. And the time that takes this relaxation is t1. At the same time, the transverse relaxation happens and it goes in this direction. So this vector goes in the minus xy direction, as you can see from here. And this is made in the time of t2. So, as you can see, this goes in this and this goes in this direction. And the second 90-degree RF pulse is applied. What happens in this part is that just after this 90-degree RF pulse, the signal is generated. How is this generated? With this formula. So at the start, the magnetization, z component of the magnetization was in here, in the z-axis. As time passes, with the function of tr in here, when we come here, the final mz, the z component of the magnetization, is here. So this mz is helping us to generate the MR image. So there is a problem with this formula. Actually, there might occur a problem with this formula. If tr is smaller than 5 times t1, then the magnetization will not be fully recovered, and thus the signal will not be fully recovered. Actually, this might seem a problem, but it will be the aim of this partial saturation sequence. This sequence is a basic and not a very common sequence, but it is useful for finding T1 values of different tissues in a slice. Let me give an example. This is a classic example MRI image, and as you can see, there are lots of different tissues, and these tissues have different T1 values. And these T1, the difference between the T1 values of these tissues will help us decide on, in an image, in a slice, whether an image region is a blood tissue or a fat tissue, etc. So let's imagine a new MR image with having 3 different tissues: muscle, liver, and fat. These tissues have different T1 values, 900 milliseconds, and so on. So, firstly, in MATLAB, I've generated a one-dimensional signal analysis of these tissues. As you can remember, the magnetization in the Z component is our main objective in here. And so let's look at the green curves. In this part, the green curve goes like this, and after the second 90-degree pulse, it goes down to the xy plane and starts to recover with T1 and etc. So as T1 goes down, for example, for fat it was 250, for liver it's 500. Also the recovered signal is a lot less, as you can see. For muscle, T1 is much more less, so the recovered signal, the magnetization in the Z component, is less than for the liver. So what happens if we increase TR to 1000 milliseconds? Let's see. For all the signals, for all the tissues, this signal generated is by far far more than the signal that has been gathered for TR equals 500 milliseconds. So that's the big difference in here. Furthermore, as you can see from the FET, you remember that it was 250 T1. And as TR is 1000, it's nearly 4 times bigger than the T1 of FET. You can see that it's nearly becoming fully recovered, but not fully recovered. If it was 5 times 250, then it might have been fully recovered. Again, for the liver, the MZ component is more than the previous analysis, but again, it's less recovered than FET because it has higher T1 value, and same for the muscle. So we can see it clearly on the 1D dimensional graphs, but what happens if you want to generate a 2D image? For this purpose, I've used the phantom imaging function of MATLAB. These phantom images are used for biomedical researches, and this is a sample phantom image. As you can see, there are different regions with different gray intensities. So let me give a new information here. In MRI images, higher the signal, the brighter the region. So I've generated much more high signal for FET, and that's why the brightest section is accepted to be FET for this project's purposes. And the second most highest signal is for liver, and the third most is for muscle. So let's accept this as the image generated when TR is equal to 500 milliseconds and go to here. Then when we increase TR to 1000 milliseconds, we are expecting an increase in the signals that are gathered. As you can see, the regions are already much more brighter. But also, I would like to observe which tissue will get the highest increase in their brightness. I'm expecting it to be fat because it gets much more higher than the liver and the muscle because of its relation with T1. So I can see from here that this one was fat, and fat got the most brightest. And then comes liver. It got brighter, of course, but not the change of the fat. And finally, the muscle part, the muscle region. It has increased a little bit in brightness, but lot less than the other tissues. So in order to do this part, I have assigned the T1 and T2 values of each pixels in these regions. For example, the pixels in this region are given with the T1 and T2 values of muscle, and then when the TR is increased to 1000, and the brightness of these images have changed with that. So this was my analysis for partial saturation sequence with one-dimensional signal analysis and two-dimensional image analysis. Thank you for watching.